In canonical transformation of the generating function, till now we have discussed already the two canonical transformation equations. First one for the first form of generating function and the second for the second form of generating function. Now today we are going to discuss the canonical transformation of third form of the generating function. So actually this derivation will also need the idea of the Legendre transformation, which we have discussed earlier. And if you have understand that second canonical transformation for the second form of generating function, then it will become very easy to understand the canonical transformation of this third form of generating function. So let us see how we can derive the canonical transformation equations for the third form of generating function. You know, the first form of generating function f1 is actually a function of small qk, capital Qk and t. And the third form of generating function, you know, it is a function f3, which is actually a function of pk, capital Qk and t. So comparing f1 and f3, you can easily say that this f3 can be obtained from f1 simply by replacing this qk by pk. When qk in f1 will be replaced by pk, that f1 will simply become f3. So I have mentioned here that f3 can be obtained from f1 merely by replacing qk by pk. Now you can see in the first form of transformation equation, we have seen that this transformation equation holds pk is equal to del f1 by del qk. We have studied this thing in the transformation equation for the first form of generating function. And if you compare this result for the Legendre transformation, then you can see instead of pk in Legendre transformation there is u, and instead of this generating function capital F1 there is small f, and at the place of qk there was x. So from this comparison you can easily say what different functions or different variables in this case will represent, which was represented by the different symbol in Legendre polynomial. So comparing with Legendre transformation, not polynomial. So comparing with the Legendre transformation, you can easily say that actually this xk is equivalent to qk here, and uk is equivalent to pk, small f is equivalent to capital F1, and g is equivalent to f3. Now you have seen in the Legendre transformation that this g is equal to f minus ux, and here actually at the place of g you can see there is the third form of the generating function f3. So you can write f3 of pk qk t equal to f is f1, and f1 is a function of qk, capital Qk and t, and ux, this will be summation over k qk pk. You can see here xk is qk and this uk is pk. And so you can say what will be f1? f1 will be f3 of this much plus summation over k pk qk. So if we will use the general equation of Hamilton to get the transformation equation, which we have used several times earlier, then at the place of f1 we will write these things f3 of pk qk t plus summation over k pk qk, and then we will get actually the transformation equation for this f3. You can see, as you know, the general Hamilton's equation of motion is this much, summation over k pk qk dot minus h minus summation over k capital pk qk dot minus h prime, and this is equal to df1 by dt. You know it. Now we will substitute the value of f1 which we have defined in this equation 1 here. So let us put at the place of f1 f3 plus summation over k qk pk. So I have substituted that value here, you can see. Now let us simplify the RHS of this equation. You can see we will differentiate this f3 with respect to t, and this type of differentiation you have done several times, so I am just writing the steps you can understand. So you know this will be summation over k del f3 by del pk, and there will be dpk by dt, and that dpk by dt I am just writing directly pk dot, and plus summation over k del f3 by del capital qk and dqk by dt. But instead of dqk by dt, I am directly writing here qk dot. You know it, qk dot. And plus del f3 by del t and dt by dt. And dt by dt, you know, this is 1, so I am not writing here 1. This is del f3 by del t. And plus, now we will differentiate this product, summation over k p qk pk. So you can see this will be summation over k qk pk dot. Actually there will be dpk by dt, and that is a pk dot, and plus summation over k pk at dqk by dt, and that we will write qk dot. Now see, in LHS there is summation over k pk qk dot. See this term. And in RHS there is also summation over k pk qk dot. So these two terms in LHS and RHS will cancel out. So what is our result? You can now see. So for getting the result, let us try to arrange the terms. See here, in LHS there is a term containing qk dot, capital qk dot, and here in RHS there is also qk dot. So now take this term in RHS in LHS, and then you can see what will be your term here. Actually, when we will bring this term in the LHS, there will be actually minus summation over k pk plus del f3 by del qk, and qk dot will be just a common factor. Qk dot will be a common factor. And again you can see in this term there is pk dot, and in this term there is also pk dot. So when you will bring this term 2 in the LHS, then what will be your what will be this term? We will take pk dot as a common factor, and again there will be, in fact both terms will become minus, so take this minus as a common factor, and summation over k, and this will be qk plus del f3 by del pk, and pk dot will be a common factor. Pk dot, this will be a common factor. And now this del f3 by del t, we will take it in the LHS. So you can see there will be h prime minus h minus del f3 by del t, and this equal to 0. Now see this equation. As we have seen several times that here this pk and capital Qk, these are independent variables. Independent variables. And since these are independent variables, so pk dot and qk dot, these will be also independent variable. So for the validity of this equation, this coefficient of qk dot and this coefficient of pk dot must be 0, and this last term should also vanish. So you can write that this pk plus del f3 by del qk, this must be equal to 0. And so we have pk equal to what? This is minus del f3 by del qk. Minus del f3 by del qk. And say this is equation 2. Minus del f3 by del qk. Now we will equate to 0 this factor qk plus del f3 by del pk. So you can see qk plus del f3 by del pk, this equal to 0, and this implies qk equal to minus del f3 by del pk, and say this is equation 3. And again you can see the last term is h prime minus h minus del f3 by del t, and that is equal to 0. So h prime minus h minus del f3 by del t, this equal to 0. And so you can say that h prime is equal to h plus del f3 by del t. In fact, these three equations, that is equations defined in 2, 3 and 4, actually these are known as the canonical transformation equation of the third form of the generating function. So equations 2, 3 and 4 are, or you can say represent the transformation equations. Transformation equations for F3. F3, which is actually a function of Pk, Qk and T. These are the transformation equations. So you can see the technique to derive these transformation equations is exactly same as you have learnt in the derivation of the transformation equation for the second form of generating function. In fact, now in the last lecture on this transformation equation for generating function, we will see the transformation equation for the fourth form of generating function.